Have you ever wondered if we could create new elements at will, expanding the boundaries of the periodic table? Consider for a moment the allure of such a possibility. Picture the periodic table not as a static chart of known elements, but as a dynamic canvas of creation, ripe for exploration and expansion. The art of creating new elements is a complex dance of particles, typically performed within the grand stages of particle accelerators and nuclear reactors. Here, scientists bombard target atoms with high-energy particles, adding protons or neutrons to the nucleus. And voila, a heavier, previously unknown element is born. It's akin to a cosmic game of building blocks, where the rules are dictated by the fundamental laws of physics and chemistry. But let's take a step further into the realm of the hypothetical. Imagine a future where scientists have developed a technology that allows for the on-demand creation of new elements. A revolutionary process that overcomes the limitations of current nuclear fusion and fission methods, which are constrained by the availability of super-heavy target elements and the immense energy required for synthesis. A world where the periodic table is not just a chart, but a palette, waiting for new elements to be painted into existence. Such a world would be teeming with possibilities. New elements could revolutionize material science, leading to the creation of materials with unprecedented properties. They could open new avenues in medical imaging and cancer treatment, and even contribute to solving the global energy crisis. But this hypothetical scenario is not without its challenges. Creating stable new elements would be a monumental task, given the instability of most super-heavy elements. Safety concerns would be paramount, as the synthesis of new elements could produce highly radioactive byproducts or require dangerous levels of energy. And then there are the ethical questions to consider, such as the potential for weaponization or the environmental impact of these new elements. It's a tantalizing thought, isn't it? But what does the reality of element creation look like today? The creation of new elements is no simple task. Today, the birth of a new element is a rare and complex event, often confined to the sophisticated machinery of particle accelerators and nuclear reactors. The process is a bit like a high-energy game of atomic pinball. Scientists fire high-energy particles at target atoms, and if they hit the bullseye, the particles are absorbed into the nucleus. This effectively adds protons or neutrons to the heart of the atom, metamorphosing it into a heavier, previously unknown element. The most recent additions to the periodic table were born this way. Meet Nihonium, Moscovium, tennessine, and oganesson. These heavyweight champions are the heaviest elements we know of, and their synthesis was a triumph of scientific ingenuity. However, their creation was anything but easy. The process of element creation is akin to scaling a mountain. It's a demanding journey, requiring significant energy and resources. The target atoms needed for the synthesis are often super-heavy elements themselves, which are not readily available. And the energy needed to propel the particles into the nucleus is immense. It's like trying to throw a pebble and hit a specific window in a skyscraper on the other side of the city. Moreover, our new elements are not known for their staying power. They are ephemeral, often decaying into lighter elements in mere fractions of a second. This fleeting existence makes them difficult to study, and even harder to utilize in any practical sense. Despite these challenges, the creation of these new elements is a testament to human curiosity and determination. It's an achievement that expands our understanding of the universe and the laws that govern it. But it also serves as a poignant reminder of the challenges we face when we dream of creating new elements on demand. It's a dream that pushes the boundaries of science, inviting us to imagine a world where the periodic table is not a fixed chart, but a dynamic, ever-expanding palette of creation. It's a dream that, while tantalizing, is fraught with challenges, both technical and ethical. These new elements, while an achievement, hint at the challenges we face when we dream of creating new elements on demand. Imagine, however, that we have overcome these challenges. Picture a world where the creation of new elements is not a sporadic event confined to specialized labs, but rather a common occurrence, made possible by a groundbreaking technology that surpasses the barriers of current nuclear fusion and fission methods. It's a fascinating thought, isn't it? In this scenario, Scientists wouldn't be restricted by the scarcity of super-heavy target elements or the massive energy requirements for synthesis. Instead, they could create new elements on demand, adding unexplored territories to the map of the periodic table. Just imagine the potential implications for science and technology. This could trigger breakthroughs in material science. New elements, each with their unique properties, could lead to the development of materials with unmatched strength, flexibility, or conductivity. Such advancements could revolutionize industries, from construction to electronics, paving the way for an era of unprecedented technological growth. And let's not forget the potential medical advancements. Imagine elements with specific radioactive properties tailored for medical imaging and cancer treatment. These could offer more effective and less invasive options for patients, transforming the face of healthcare as we know it today. Besides, if these new elements could facilitate more efficient energy transfer or storage, they might provide solutions to the global energy crisis. We could be looking at the development of high-capacity batteries or new clean energy sources, contributing significantly to a sustainable future. The potential advancements sound promising, but they don't come without a price. The on-demand creation of new elements would undoubtedly bring about a paradigm shift in our understanding and application of chemistry and physics. Still, we must remember that with great power comes great responsibility. The ethical considerations, safety concerns, and challenges of stability would need to be addressed. But that's a story for another time. For now, let's revel in the possibilities that this hypothetical world of new elements could bring. The power to create comes with its own set of challenges. Imagine being able to synthesize elements on demand. As tantalizing as this scenario may be, it is not without a host of challenges and considerations. The first hurdle we would face is the problem of stability. Most of the super-heavy elements that have been synthesized so far are highly unstable, often decaying in mere fractions of a second. The creation of new, stable elements would be a monumental task, requiring a level of precision and understanding of atomic structures that we have yet to attain. Another significant concern is safety. The process of creating new elements could potentially produce highly radioactive byproducts. Think about the immense levels of energy required for such synthesis. These would pose substantial risks, not only to the researchers working on these projects, but also to the environment. We'd need to devise stringent safety measures and robust containment protocols to manage these risks effectively. Now, let's not forget about the ethical questions that such a power would raise. The potential for weaponization of new elements is a grave concern. Imagine elements with destructive capabilities falling into the wrong hands. It's a chilling prospect. And then there's the environmental impact. The creation and use of these new elements could have unforeseen consequences for our planet. We'd need to tread carefully, considering the ethical implications every step of the way. This hypothetical scenario also raises a philosophical question. Just because we can do something, does it mean we should? It's a question that scientists and ethicists alike would need to grapple with. And it's a question that we as a society would need to answer. These challenges highlight the responsibility that accompanies such power. The power to create new elements would be a tremendous boon for science and technology, but it would also require us to act with the utmost care and responsibility, considering not only the potential benefits, but also the possible risks and ethical implications. In essence, with great power comes great responsibility. The on-demand creation of new elements might still be a flight of scientific fancy, but it's a concept that stirs the imagination. Imagine the advancements in material science, the breakthroughs in medical treatments, and the solutions to our energy crisis. But with these possibilities come significant challenges: the stability of these new super-heavy elements, the safety concerns around their creation, and the ethical considerations of their potential uses. This power to create new elements on demand would rewrite the rulebook of chemistry, redefine our understanding of physics, and reshape the landscape of technology. It would push us into a new era of scientific discovery, where the periodic table is no longer a static chart, but a dynamic canvas for creation.